Hi everyone, so here's our first example on moments and equilibrium. We're going to look initially at uniform rods. So uniform, straight away, that's a really important word that we see in the question. That means that the weight is going to be acting exactly at the centre of this rod. Okay, so a uniform rod AB of length 4 metres and mass 5 kilograms, so that mass is going to give us a weight of 5G, acting at the centre of the rod, is pivoted at C, where AC equals 1 metres. Now, quite often in the question, they'll give you the diagram. For these first couple of examples, we're going to draw the diagram ourselves, but quite often, as I say, the diagram's given. And we're asked to calculate the mass of a particle which must be attached at point A so that this rod remains in this horizontal equilibrium position. So let's just draw this diagram first of all. So we've got a rod AB. Oops. And that's got length 4 metres. It tells us it's uniform, so exactly at its centre then, we're going to have our weight acting. So that's going to be our 5 times acceleration due to gravity, so 5G. And we're also told there's a pivot point at C where AC is 1 metre. So this bit here is going to be 2 metres. So C is going right in the middle here. So there's our sort of seesaw pivot point there. There's point C. And that's going to be 1 metre. So that must be 1 metre as well, which means that this is going to be 2 metres. Okay, so there's my diagram. Calculate the mass of a particle which must be attached to A to maintain equilibrium. If we think about this sort of practically, if this was, I don't know, a seesaw or whatever, if we had a pivot point here and we just left this with the weight here, then obviously this is going to go this way, okay? And then it wouldn't be in equilibrium because as soon as we let go, it's going to go like this. So we're looking to put a weight here on A that balances the whole thing out and keeps it horizontally in equilibrium. So I'm just going to call that mg, and we're going to be trying to find out this mass m here. Okay. Now the other force that we need to put on is a reaction force at C, because what's happening here at C is we've got this rod, this uniform rod, and it's touching this point C. So here it's resting on here, so the weight of the rod is going to be pushing down, and so we've got the reaction force back up at C, a bit like we've seen reaction forces on the feet of a man in a lift or something like that. So we've got this reaction force at C pushing up, if you like, on this. Obviously, it's not making it move, but it's definitely still there, that reaction force. So we need to put that on there. So our reaction force at C. Okay. So let's have a look at this. And the way that I'm going to do this, you can take moments about any point. I'm going to take moments about point C, because if I do that, this reaction force won't have any moment effect, won't have any turning effect. The moment about C of this will be 0. So I don't need then to have this in my calculations. And we'll have a little think in a minute at the end of the question. If I did need that in my calculations, what would I do? But let's do this. So let's tell the examiner what we're doing. We're going to take moments about point C. And I'm doing that so that I don't have to worry about this reaction force. I'm not asked about it in the question, so that's okay. Tell the examiner which way I'm taking. So I'm going to take clockwise as positive. So which way am I taking as positive? And then we're going to take moments about C. So again, thinking about what we did yesterday and thinking about which way things are going to turn, this mg force is going to be pulling downwards, so that's going to be going anti-clockwise. That's going to have a negative moment if I'm taking clockwise as positive, and this 5G is going to be pulling this way, so that's going to turn clockwise. So that's going to have a positive moment effect. So looking at this one then, the moment here is going to be negative because it's anti-clockwise, this movement, minus mg is my force, and my perpendicular distance is 1. And then the 5G, that's going to be causing a positive clockwise turn. So that's plus, my force is 5G. My distance from my point C is 1 metre, again, that perpendicular distance. And that's going to equal 0 because the sum, we've seen from those notes earlier, the sum of my moments must be 0 if it's in equilibrium here, because equilibrium means there's no resultant turning effect. So this is because it's in equilibrium. Okay, so let's just carry on with this. So minus mg plus 5g is equal to 0. So if I take these over, I can divide by g. So m is going to be equal to 5, and it's kilograms because it's mass. And that's that question done. It's just a fair sort of basic, straightforward example to illustrate these methods. Now, to get RC involved, if I did want that, if I wanted the reaction at C, I could take moments about some other point, or even simpler, I can look at vertical movement here. I can resolve our forces vertically, because again, in that definition in our notes of equilibrium, we said that the resultant force in any direction must be 0, as well as the sum of the moments being 0. So here, I could take moments about B, for example, or this point in the centre, or A, and that would get my reaction at C involved. Or I could just have a look at resolving vertically, and if I did that, if I resolve vertically, then what's happening? If I take up as positive, then upwards, that reaction force is happening. Downwards then, so minus mg, and downwards minus 5g. And again, that must be 0 because my resultant force must be 0. So the reaction force there must be equal to mg plus 5g. And you could have just written this down straight away without this, but this is about our resultant force equals 0 part. And then if we needed to in the question, we could, have a look at working out what the reaction was, etc. Okay, so that's example 1. Let's have a look then at example 2. Okay, so example 2, now we are going to have a look at having our reactions involved and at finding those. So uniform, again, uniform really important in questions, and we are going to move on obviously to non-uniform as the next section. But uniform beam AB of mass 30 kilograms and length 5 meters rests horizontally in equilibrium, and now it's on 2 supports C and D, and it gives us some information about where they sit in our diagram. A man of mass 75 kilograms stands at a point E, and again it tells us where this point E is. And sometimes they won't. Sometimes you'll have to just put, a point on your diagram and work out the distances, let's say. So by modelling the beam as a uniform rod and the man as a particle, so there are modelling assumptions, we've seen them before in other questions. Calculate the magnitude of the reactions now at each of those supports. So let's draw a diagram, and again, as I say, quite often the diagram's given, but if it isn't, we need to make sure we're okay at drawing them. So we've got our beam or our rod AB. It tells us that it's uniform, so this mass must be acting in the middle. So there's my 30. G as a force acting down there as the weight. And we're also told what we told, that the overall length is 5 meters. So let's put that on. So my overall length is 5 meters. And then we've got these pivot points at C and D, where AC and BD are both 1 meter. So coming 1 meter in here, I've got my pivot point C. So that's 1 meter. And here I've got my pivot point D. And again, that bit there's 1 meter. The last bit then, let's put this on. The man of mass 75 kilograms stands on the beam at point E, where AE is 2 meters. So A to E now is 2 meters. So this is definitely not to scale, look, but anyway, there's 2 meters there. And I've got my man, and I'm going to just draw him as a particle because that's what it says to do. You can draw a little man if you want. But there we go, there's our man. And his weight is 75 G. So our mass, 75 kilograms times our acceleration due to gravity. So now I can put some other lengths on. So AE was 2 meters. So this point here is E. So AE was 2 meters. So we've got here 1 meter and here 0.5 meters. And then this, because this whole thing's 5, this is going to be 2.5. This is 1, so this must be 1.5. So I'm just putting those on my diagram so I don't need to worry about them when I'm looking at my moments a bit later on. Okay. What else do we need? Well, these things, this rod is sitting on these pivots, so these pivots are going to have upward reactions. So we've got our reaction force at C there, and then we've got a different reaction force at D there. And sometimes people make the mistake of assuming that those reactions are the same, but they won't be, because if you look at this one in particular, here we've got more weight acting down on this side of the rod than on this side. So that's going to make a difference to these reactions, and it's going to mean this reaction at C is going to be bigger than this reaction at D because there's more downwards motion going on here, or more downward force, sorry, should I say. Okay, and what I'm going to do here, I am going to do that vertically idea. We don't need to, but I'm going to do vertically just so that you can see how that would work. So if I look at vertically, well here, you know, there's no motion vertically, it's in equilibrium, so the resultant force must be 0 because it's in equilibrium. And if I take up as positive, just to tell the examiner what I'm doing, I'm going to get R at C, the reaction at C positive, plus the reaction at D positive, and then negative going downwards. I'm going to have this 75G and this 30G, and that resultant force must be equal to 0. And you can write that, you know, you don't have to write that line. You can kind of, you know, just write upward forces equals downward forces. That way, that's fine as well. It means the same thing there, obviously. Okay. And so looking at that, what have we got? Our two reactions added together are going to give us 105G. I'm just going to call that equation 1 because we're going to refer back to that in a second. Okay, now I'm going to take some moments to get these reactions involved in a different equation. And again, because if I take a moment at a point where a force is acting, the moments there are going to be equal to 0 because the distance is 0, then I can get an equation with just, if I take moments at C, it'll just have RD in it, the reaction at D in it, or if I took moments at D, it would just have RC in it. Or if I took moments anywhere else, it would have both of these in. So there's lots of different ways of doing these questions. But let's have a look at taking moments about C so that then we're eliminating this variable RC from our equation. So let's tell the examiner what we're doing. We're taking moments about C. Okay, and then the moment effect, as I say, of RC is going to be 0. It has no effect there, no turning effect. So let's take clockwise as positive. Telling the examiner that's what I'm doing. So now let's have a look at C clockwise. So this 75G and the 30G are both pulling downwards, so they're going to go clockwise, but this reaction at D is tending the other way, so that's going to be an anti-clockwise. Okay, so let's have a look at doing that. So my 75G force is 1 metre perpendicular away from C. My 30G force, this weight here, is 1.5 metres perpendicular away from C, and then this reaction force upwards is anti-clockwise, so that's negative, and then my distance here, let's be careful now, we need to make sure I'm doing it from C, so from C, this distance is going to be 3 metres, and that all equals 0 because the sum of my moments must be 0 here. Okay, so let's sort this out. 75G plus 45G minus 3 RD is equal to 0. So 120G is 3 times that reaction at D. So the reaction at D is equal to 40G newtons. And then just get our calculator out and we could leave it like that. If the question wanted the answer in terms of G, or times by 40 by 9.8 is going to give me 392 newtons for that reaction force there. And then the reaction force at C, I'm just going to move this up a little bit. The reaction force at C, we can now just use this equation 1. So I can sub into equation 1 here and say, so now RC plus my 40G is going to be equal to my 105G from this. So my reaction at C is 65G newtons. And again, depending on the question, if it wanted the actual value rather than in terms of G, that's going to give us 637 newtons. Okay. Now we could here, you know, I've just taken two moments about C. We could take moments anywhere, and I'm just going to, over on this side, just take moments about D, just to show you that that would have worked as well, and, you know, maybe as a check. So let's have a look at here. If I did that, if I take moments about D, again, I'm going to take clockwise as positive. Then about D, at this point here, this reaction force now is not having any turning effect at all, so no moments there. This reaction force at C is pulling my sheet of paper that way, so that's clockwise, whereas these two are pulling this way, so they're both anti-clockwise. So let's have a look at putting that in here. So that would give me the reaction at C times this distance to D, which is 3. And then minus 75g, because that's causing an anti-clockwise turn. The distance to D of that one is 2, minus my 30g, and the distance is 1.5. I've run out of paper a little bit, but that's equal to 0. And then sorting this out, 3RC minus 150g minus 45g is 0. So that's going to be 195g over 3, which is 65g. So that definitely does work. So we can do that as a check, or, you know, we could have taken moments about D, or in fact about any point for this. So we could have done this a different way if we'd wanted to. Okay, so there's 2 examples on uniform rods and equilibrium. And so I'd like you to do a little bit of practice on that now for the rest of the lesson and a bit of independent study. And I'll put this all on Firefly.